Hello, good evening everyone. It's my huge pleasure to introduce Thierry Foglizzo, our esteemed colleague. Thierry is an astrophysicist at Saclay, France, and he made a very important contributions in the field of supernova explosions, in particular in understanding of how supernovas explode. And this is what he's going to talk about. Welcome.
Thank you very much. First, I would like to thank Ernazar for his invitation. I'm very honored to speak in your science cafe. So I will try to explain what I understand of the explosion of massive stars, and maybe a good way to get familiar with the complicated physics, I mean sometimes complicated physics that is taking place at the center of a star at the moment of its death, is to realize that a large part of what's happening there can be understood simply by looking at water flowing in a fountain. And that's the good surprise of this field of physics. So there is this fountain here, which I will show you in more details later. And the fluid dynamics which takes place in this fountain happens to have very strong connection, very strong similarity. It's even an analog to the fluid dynamics which takes place at the center of a star. So a star is made of gas, and the gas follows the laws of fluid dynamics. Water is a liquid, and a liquid follows the laws of fluid dynamics. And there are strong similarities between the two. I don't know if you have a pointer, or maybe this. Maybe I don't need one. It's okay. So I will assume that you're not that not all of you are familiar with the physics of stars, but maybe you know that stars evolve. Stars are born from the contraction of the interstellar gas. They are made of hydrogen mainly, and during their life they produce energy by reactions of nuclear fusion. So they assemble atoms of hydrogen into heavier atoms like helium, and if the star, and that's what the sun is doing at the moment. And if the star is massive enough, it means that it has a strong enough gravity. It's able to assemble atoms further than what the sun is currently doing. And after assembling helium, the star is able to assemble carbon, oxygen, and heavier elements. And some stars die in a very spectacular manner, and that's what we call supernova. So here we have an illustration of the most famous supernova in our galaxy. It's called SN 1987A because it exploded, when it was observed on the Earth in 1987. And it was really the beginning of supernova theory, or a big investment in supernova theory, because for this particular supernova, people were able to detect on Earth some particles which are called neutrinos. So I don't know how many of you are familiar with neutrinos. Can you raise your hands? So neutrinos are very light particles. Their mass is close to nothing, and they are very fast. They travel at the speed of light, and they can go through the Earth, they go through your body without even noticing it. It's very difficult to detect a neutrino. And neutrinos are emitted during the explosion of a supernova, and it was the first time that they were detected. Such explosions take place every night, but they are so far away in distant galaxies that they are too far to be able to detect a significant flux. Since it's so difficult to detect neutrinos, you need the source to be close enough. And so when we see supernovae like this in distant galaxies, we see a very significant increase of light. I mean, the supernova explosion can be as bright as the full galaxy, but still it's too far to have neutrino detection. And the this supernova is famous not only because of neutrinos, but also since it was so close, people were able to follow its evolution in great details, to follow the light curve in different wavelengths from X-ray, gamma rays down to radio wavelengths. So this is the astrophysical part, and the simple part is hydrodynamics of water. And so to avoid any confusion, because this fountain I'm going to talk about is not going to mimic an explosion. You're not going to see an exploding fountain. So I'm immediately going to show you what can be observed in this fountain. And you will see that it's pretty simple. It's a wave. You will see a wave which rotates here in a stationary manner. So the fountain will look like that. So you won't see much more than that in this fountain. But you will understand little by little that what you see here contains a lot of physical insight into the physics of supernovae. So this fountain injects water from the outside to the center. And so this flow of water in the fountain will mimic the collapse of the core of a massive star. I would like you to interrupt me as soon as you have a question, so that it will make the interaction more interesting for you and for me. So don't hesitate to ask a question, even if you think that the question may be too simple. I'd be glad to answer it. So maybe you've heard of supernovae because they are very fashionable, especially in cosmology. And so I'd like to distinguish right now the two types of supernovae that people study. So here on the left side, you have three remnants. Once the supernova explodes, it ejects some gas in the interstellar medium. And so we call this a supernova remnant. And these three remnants are historical supernovae that you can observe in our galaxy. So this one exploded for example, this one exploded in 1572, and it was observed by Tycho Brahe. This one was observed by Kepler. And those are also historical supernovae with 87A, which I just mentioned. So this is a very zoomed-in view of the supernovae. Actually, the ejected matter is contained only in this region, and this ring here was there before the explosion. It's before the star exploded. There was a structure around the star because it was probably there was probably a strong wind and a binary system, which produced this ring of dense matter, and this dense matter became luminous because of the explosion. And so Cassiopeia and the Crab are very famous supernovae. And the distinction between these two types is that those are the ones which I'm going to talk about. Those correspond to the death of a massive star. So when I say massive star, I'm talking of the stars which are at least 10 times as massive as the Sun. So maybe you know that the Sun will not explode as a supernovae. The Sun is not massive enough. So do you know how the Sun will explode? Will die? Yeah, it will make a white dwarf, exactly. So it will inflate, the envelope of the star will inflate, but not in a violent manner as a supernova. And the core will collapse, but not as violently as in a supernova. And it will produce what we call a planetary nebula. It has nothing to do with planets, but it's a very beautiful extension of ejected gas, which can be observed. And on the left side, those are called supernovae, and those are the ones which are so precious to cosmology because those explode in what we call a standard manner. So their luminosity can be scaled to recover the distance at which the supernova took place. So those are used to measure the universe and so to infer the global structure of the universe. but those are not due to the same mechanism as the death of massive stars. Those are due to the explosion of a white dwarf, as you said. So we won't go into the details of the physics of white dwarfs, although you will notice that what's taking place at the core of a massive star is really, I mean, the process which initiates the death of a massive star is the same as the process which initiates the explosion of a white dwarf. It's really, you have, when you have a mass of gas which is too massive to maintain an equilibrium against pressure forces, when you have a mass of gas where the pressure is due to quantum mechanics, it's called the degeneracy pressure of electrons, of relativistic electrons. So this is, it's a bit complicated when you say it like that, but it's a state of matter. When matter is dense enough, it's the last way that matter can resist gravity. And in the case of a white dwarf, the white dwarf is made of carbon and oxygen, and it will produce, if it approaches a critical mass, it will produce a thermonuclear explosion like this, with a lot of energy liberated by the combustion of this carbon and oxygen, the fusion of this carbon and oxygen. It's an explosive process. Whereas here, you have a similar threshold, which is reached, but instead of carbon and oxygen, the core of a massive star is made of iron, essentially of iron. And iron cannot produce energy through fusion reactions, contrary to carbon and oxygen. And so in this case, the star will, the core of the massive star will collapse, but instead of igniting fusion reactions, the outcome of this collapse will be very different from this one, and that's what I'm going to describe. But the initial moment when the explosion starts corresponds to a mass of gas which reaches a threshold where where the pressure can no longer resist against gravity.
How far are these supernovae? How far from the Earth?
So in the whole universe, so the supernovae can be observed at cosmological distances. So you know that there are different methods to measure the universe. So when the stars are close enough, you can estimate their distance simply by some parallax effect along the orbit of the Earth. You can see the star moving against the background. So this is a way to measure distances in the local galaxy around us. But when you, and there is another domain where you rely on Cepheids, on the variability of some stars which have some relation between their variability and their luminosity. Those are called Cepheids. And on the longer on longer distances, you rely on supernovae, where you have a relation between the light curve of this object and the duration of the light curve. I mean, the total luminosity of this object and the duration of the luminosity curve, you have a scaling relation which enables you to recover the exact absolute luminosity. And if you have the absolute luminosity, you recover the distance. So those are observed up to cosmological distances.
A few light years away?
Oh, much more, no, much more. It's millions of light years. It's yeah. I cannot tell you the exact maximum, but yes, it's cosmological distances. Maybe Ernazar, you would know the exact maximum, the highest redshift. When distances are cosmological, you measure the redshift, and yes. Yes, it's very distant. Those are observed in galaxies where you don't even see the galaxy. The galaxy is so faint, you don't really see it, and suddenly the explosion of a supernova makes it visible. So those are very, very distant galaxies.
And what is the color, the meaning of the colors you put there? Is there a meaning?
Yes. So yes, you're right to ask this question. So those supernova remnants are usually visible in X-rays. So for example, the most famous one is the Crab Nebula, which is observable in visible light by amateur astronomers. And on top of it, this blue color is the X-ray observation. So when you observe in X-ray, you just choose a color, an artificial color for your image. This is visible light. So for example, this is also X-ray superimposed onto UV, and so those images are the best details we can find, but with a mixture of different instruments in different wavelengths. So some of them are invisible in visible light, but visible in X-rays. So depending on the color here, you will see it will carry the signature of different elements like iron or oxygen. So this is how the colors are useful. It's to distinguish the different temperatures and the different elements. So for those gravitational, yes?
So Kepler saw this supernova in 1604.
Yes.
And we still can see it, right?
Yes, yes. This is an image you would observe today. Because those images were produced by the most advanced instruments, so the most recent instruments, and those remnants evolve on very, very long time scales. So this one is really maybe an exception compared, because this is evolving on a short time scale because it exploded very recently. So this shouldn't be called a supernova remnant yet. It's in the process of becoming a supernova remnant. But these remnants will evolve very slowly over hundreds of years, and the oldest remnants, I mean, slowly they lose their very well-defined shape, but for example, there is a remnant in the Cygnus loop, is a very old remnant, which is thousands of years old. So yes, those, and there is a very big range of time scales in this physics. So here, when you look at remnants, you're talking of hundreds of thousands of years. But when you're dealing with the explosion itself, we are going to deal with seconds, with milliseconds. So the physics of supernovae covers a very wide range of time scales. So this is what you observe today. So those pictures I showed looked pretty spherical. But there is one important ingredient in modern theory of supernovae. It is the idea that the explosion is not spherical at all. And this is a very central idea which justifies the use of complicated numerical simulations to study those objects in 3D rather than assuming a spherically symmetric evolution. And there are some observational hints that indeed we should not assume that the explosion is spherical. And one of those hints is the velocity of neutron stars. So I don't know if you've heard of neutron stars, but so neutron stars are very dense objects. They are, in a way, dead stars. They are called neutron stars, but they are really the outcome of the life of a massive star. So when a star reaches this threshold, and when the mass of the core of a star reaches a threshold which is called the Chandrasekhar mass, which is about 1.5 solar masses, then this stellar core collapses up to a new equilibrium. And this new equilibrium will be a neutron star. So the core of a massive star, I said, is made of iron, and iron atoms are going to be compressed by gravity, reach very high densities, and those atoms are going. So you know that atoms are made of a nucleus and some electrons, and the nucleus is made of protons and electrons, protons and neutrons. Sorry. So you have charged particles, which are the proton and the electron, and you have neutral particles, which are the neutrons. And as the star collapses, the charged particles are going to disappear through a reaction which takes one proton and one electron and gives one neutron and one neutrino. I don't know if you've heard of this reaction which is called electron capture. So you have a transformation of matter from a state of a nuclei made of proton, neutron, and electrons to a new state of matter made of neutrons, essentially neutrons. And this is what we call a neutron star. And neutron stars are so dense that for 1.5 solar masses, as I said, it takes only 10 kilometers to contain this mass. 10 kilometers. So I don't know who in this audience knows the size of the sun. The sun is 1 solar mass. And does anyone have an idea of the size of the sun? How many kilometers?
In units of Earth, it's 300,000 times the volume of the Earth, right?
Yeah.
So,
You said?
I mean, in units of the size.
In units of the Earth's radius?
It's around 300,000.
So it's maybe. I measure it in kilometers. So the solar radius is 700,000 kilometers. So I'm not sure we will find the same answer, because the Earth is 6,000 kilometers. So it's about 700,000 kilometers. It's yeah, slightly more than 100 times. And so that's 700,000 kilometers. And here we're talking of a neutron star, which is heavier because it's 1.5 solar masses, and it's just 10 kilometers. So it gives you an idea of the density of a neutron star. Remembering that density scales like the size to the cube, so it's very, very dense. But even a neutron star, so a neutron star is an equilibrium of neutrons really touching each other. But even this state of matter cannot resist gravity if the mass of a neutron star exceeds a certain threshold, which is not very well known, but which is somewhere between 2 and 3 solar masses. So if you try to accumulate neutrons in a neutron star, there is a threshold when, again, this equilibrium is going to collapse because gravity is too strong, and then you will form a black hole. So the neutron star is the last possible equilibrium that we know of before the formation of a black hole. And a black hole is a collapsed object where actually gravity is so strong that the velocity it would take to escape this gravity would be larger than the speed of light. So there is no way to escape a black hole because there is no sufficient escape velocity to get out of this attraction. So here we are talking of a massive star which generates a neutron star, and maybe if the mass accumulating on this neutron star is too high, it will produce a black hole. But in many cases, it does not produce a black hole, and we know that because we observe neutron stars. And this is an example of a neutron star here. And neutron stars are known to have extreme velocities, extreme densities, and they are known also to have extreme velocities. So here, at the tip of this shape here, you have a neutron star which is traveling very fast in the interstellar medium. And most neutron stars are very fast. This is the fastest, so it's possibly 1,600 kilometers per second. This is an extreme velocity. Most neutron stars have velocities of between 200 and 300 kilometers per second. And this has been a puzzle for 50 years. Why are neutron stars so fast in the galaxy? And you will see that the answer to this question is related to the physics of the explosion of a massive star and is related to what's happening in this fountain. So this is the velocity distribution of neutron stars, and this is a logarithmic scale, so you see that most of them have velocities around 300 kilometers per second. So the fact that neutron stars are so fast is a hint that maybe the explosion is not symmetric, because if the star was, because most stars are much slower than that. The stars in the galaxy are typically 30 kilometers per second. If you subtract the orbital velocity of stars in our spiral galaxy, I mean, orbital velocities are about 200 kilometers per second. For example, the Sun orbits the center of the galaxy with 200 or 250 kilometers per second. But the dispersion of velocities of stars in the galaxy, so some are going slightly faster, some are slightly going in the perpendicular direction compared to the galactic plane. These dispersion velocities are 30, 50 kilometers per second, whereas pulsars have velocities which are 10 times faster. So this is a hint that maybe the moment when neutron stars are born is a moment when the explosion is not symmetric. Sometimes I say neutron star, sometimes I say pulsar. These are the same objects. A pulsar is a neutron star which rotates, and usually pulsars are detected by the radio signal which is pulsed due to the rotations. This is how they have been discovered. So this is the sketch of the physics of the explosion. I mean the mechanism of the explosion. You start from a huge star, 600 million kilometers in diameter here, where the center, so it's called a red supergiant star, which was not that big at the beginning, but it inflated before its explosion during the red supergiant phase. And at the center, you have this iron core, which is about the size of the moon, or I mean, it's a few thousand kilometers. But the mass of this object approaches this critical mass of 1.5 solar masses. And when this threshold is reached, in less than a second, this object, which is about the size of the moon, in less than a second is going to shrink into we call it a proto-neutron star. It will become a neutron star when it's cold. Here it's still very hot and slightly bigger than a neutron star. So it's here it's 50 kilometers in diameter. Actually, it's 50 kilometers in radius, and then it will slowly shrink to 10 kilometers in the end. So you have to imagine an object the size of the moon, but the mass of heavier than the sun, collapsing in half a second into a proto-neutron star. And this object which collapses was supporting all the rest of the star. So here we start from a star which is 15 solar masses. So this is 1.5, and so there are 13 solar masses sitting on this iron core, and suddenly these 13 solar masses are not sitting on anything, and they are going to fall freely towards the center. And it's this rain of matter which is falling onto, towards the center, which somehow has to be convinced to change its direction, to change a collapsing motion into an explosion. This is the challenge of supernova theory, and this is this hasn't been a success for a long time, because it's very difficult to convince matter falling very fast. The velocities which are reached are close to 1/10 of the speed of light, so it's very, very fast. And somehow we know from the observations, from the fact that we see explosions in the sky every night, we know that somehow this matter has found a way to reverse its motion and explode, because in the end we will have simply a neutron star, which is 1.5 solar masses, and the rest of the matter will be dispersed, as in the pictures we saw about the supernova remnants. So this is the puzzle. And the part of the physics we think we understand is the fact that as iron is falling and reaching very high densities, we have this reaction which takes a proton and an electron and makes a neutron and a neutrino. So we know that the iron matter is going to be changed into neutral matter made of neutrons. So when you fall and meet a very dense wall here, of course it produces a shock. It's like running against a wall. There is no doubt it will produce a shock. And in fluid mechanics, it's called a shock wave. And the connection to the fountain is going to deal with this shock wave, which actually, shock waves are rare on Earth. I mean, you have a shock wave when you have a supersonic airplane, faster than the speed of sound. But you don't meet shock waves every day in your everyday life. But what you meet every day in your everyday life is the analog of a shock wave in water. So that's what we're going to see. Yes?
What happens to the rest of the massive stars, hydrogen, helium?
So on this very short time scale, hydrogen and helium did not even notice that something was happening. They are just sitting on oxygen and carbon, and they don't even know. But if the explosion is successful, so if somehow this inner region manages to change direction and go outward, then this shock wave is going to propagate, and it will take hours for this shock wave to propagate through this star. And so at some point it will enter the helium region and then the hydrogen region and push this matter out to produce the supernova remnant that we saw at the beginning. So now I'm going to focus on this very, very inner region where matter has to change direction. But once the shock wave is launched in this very inner region, it will travel for hours, and the real difficulty is to go out of this very inner region. It's like, I don't know if you have this image of a potential well. Sometimes people draw a black hole as a very deep well, and it's really a good illustration of the shape of gravitational potential. So if you are very deep in this potential, it takes a lot of energy to go out of it. And the further you go, the easier it gets, because then the slope of the potential gets flatter and flatter. And so this hydrogen region is in the very, very flat region of this gravitational potential. So if you manage to escape the very deep inner regions, you will easily escape from the outer regions. So modern simulations have allowed us to see the dynamics of this collapse So the first simulations, which were really encouraging, were performed in two dimensions. Here you have an axisymmetric simulation. It looks like 3D, but actually you have an axis of symmetry here. And here you see the surface of the shock wave. So in blue, you have all the matter flowing towards the center. And this is the neutron star in the middle. And the surprise is that this spherical shock wave doesn't stay spherical. You have all these complicated motions where you have small-scale convective motions and you have a kind of large-scale oscillation of this shock wave. And the time is indicated here. The full simulation is less than a second. So here it lasts a long time because it's a computer. But everything you see here will last less than 1 second. In 1 second, you have those oscillations. You have about 30 oscillations per second. So it's a very fast motion. And the size of this simulation can be seen here. So these are kilometers. So as the explosion starts here, so we are still in the very inner region of the star, but we are dealing with distances which are a few hundred kilometers. So at the beginning, it was 150 kilometers in radius, and maybe in the end, it's 500 kilometers in radius. But this is considered as a successful explosion. It's a successful beginning of an explosion. But as I said, if it begins like that, there is no doubt that it will continue successfully. So now we have seen enough complicated things, and let's go back to water. So here is what should be familiar to you. So when you have water flowing in a kitchen sink, here you observe this circle about this size, a few centimeters, 10, 20 centimeters, which is a sharp transition between water which flows very fast in a thin layer and water which is slower in a thicker layer. And so this is called a hydraulic jump. So who has seen this in a kitchen sink? I guess everybody has seen this in a kitchen sink. Not everybody? Some people have never seen this? Come on. So this is called the hydraulic jump. This is the circular hydraulic jump. And this sharp transition between a fast flow and a slow flow is really what's happening through a shock wave in a gas. In a shock wave in a gas, the kinetic energy is suddenly transformed into heat. And here, the kinetic energy is suddenly transformed into potential energy. It's a thicker layer of water. So there has been a transformation of kinetic energy across this hydraulic jump. And the dynamics of this hydraulic jump follows some equations which are the same, very similar to the equations of a gas crossing a shock. So the idea of this water fountain is to push this analogy further and to let water flow along a surface which mimics gravity. I told you about this picture of a gravitational well. So here you have the scheme of this gravitational well. You inject water from the outside in the same manner as gas is flowing from the outside towards the center at the moment when the proto-neutron star forms. And the nice thing about this analogy is that everything related to compression in a gas is going to be related to a change of depth in water. So water is incompressible, but the variation of depth in water are going to mimic the variation of density in a gas. And these variations of density and pressure in a gas are responsible for the propagation of acoustic waves. The reason why you can hear me is pressure waves propagating from me to you. And in water, you have also waves at the surface of water which propagate in the same manner, following similar equations to those describing acoustic waves in a gas. So when you start injecting water from the outside, so you see water flowing, there are bubbles which visualize the flow of water. You create, there is an obstacle at the center. There is a cylinder at the center which prevents water from immediately falling into the central hole. And this boundary here, this vertical cylinder, is responsible for creating this hydraulic jump. So this is the opposite experiment compared to what's happening in your kitchen sink. Instead of water flowing from the center towards the exterior, here you have water injected from the outside going towards the center. And the surprise is that despite the fact that water is injected in a very stationary and uniform, homogeneous manner, you have this unstable motion which appears. So I don't know how familiar you are with instabilities, but an instability is something where you would have imagined that you had all the ingredients to produce an equilibrium. Is as if I try to put this bottle, well, this is a stable equilibrium. If I try to make an equilibrium like this, you can find a point where you have a balance of forces, but it's an unstable equilibrium, and any small motion will get amplified, and you will find a new equilibrium. And here, when you have a flag in the wind, you could imagine that the wind can flow on both sides of the flag, and the flag could stay in principle perfectly symmetric, but you have an instability which generates transverse motions. So this is another example of instability. And here, you could have imagined that this hydraulic jumps would have stayed perfectly circular, or approximately circular, but some instability makes it oscillate and then rotate. And I draw your attention to this piece of metal in the middle, which is very light and passive. It doesn't. It just follows the motion of the fluid in the inner region, and you will see that after some oscillations of this hydraulic jump, this hydraulic jump decides to rotate in one direction, and the inner region of the fluid starts rotating in the opposite direction. So you see that the hydraulic jump is going to rotate clockwise here, or not. Yes, here you see it rotates clockwise, and the inner region of the fluid rotates anti-clockwise. So this, as we will see, is related to, is an important property to infer the spin direction of neutron stars. Because, yes?
So I guess you repeat this experiment several times, and is it always water rotating clockwise?
No, it's random. Theoretically, it's random. If the experiment is, an experiment is never perfect, so it's possible that the experiment prefers one direction because the injection is not perfectly homogeneous. But this particular experiment, when it's well balanced, it gives really random directions.
But the motion of the water in the center is always opposite, yes?
Yes, always opposite. Yeah.
Does the diameter of the cylinder change the result?
Yes, that's a very important ingredient. The ratio of this diameter and the diameter of the hydraulic jump at the beginning is a very important ingredient. If the two diameter are too close, if the hydraulic jump is too close to the cylinder, then the instability is not prefers some small scale motion. There is no longer a large scale instability.
And in your situation, the diameter should become smaller, right? If it collapses.
It shrinks. You're right. Yeah, yeah. It shrinks on a slow time scale, but it does shrink. Yeah. So I would like to emphasize the fact that this fountain was built in my garden, and this should encourage you to investigate yourself the laws of physics, because you can discover things with very simple tools and equipment. So look, you can see in May 2010, I was trying to make this experiment. I was just using water hoses, and I was trying to get a uniform injection of water. So I put more pipes, and in a few months, you see, from May to November, I obtained results which were published in PRL. PRL is an American Journal of Physics. It's called Physical Review Letters, and it's one of the best journals of physics. So I think it's very important to remember that you can reach PRL, I mean scientific publications of international standard with simple ingredients. And then after that, after those results were obtained, my institute was convinced that it was worth building this fountain with professional equipment so that the accuracy would be better. So this is what it looks like now. So when you do this experiment, you want to check that it's not by chance that this oscillation appears. So we do numerical simulations. So here is a numerical simulation of the experiment, and here is a numerical simulation of the star. So this is gas dynamics, and this is water dynamics. And so you see that in the case of a star, of a shock wave in a gas, you observe an oscillation and then a kind of rotation. And in the case of water, you start with an oscillation and then you break another time the symmetry, the oscillation symmetry, and then you begin this rotation. So the similarity between the simulation and the experiment proves that there was no, I mean, the construction of the experiment was good enough. It was not completely dominating the evolution. And the similarity between the simulation and the gas dynamics tells you that what's happening in the fountain is due to the same physical mechanism as what's happening in a gas, using this analogy between hydraulic jumps and shock waves. This is just a movie, but then it's motivated by writing the equations, and the equations indeed are similar.
Excuse me.
Yeah.
What is the frequency of this oscillation?
Which is the cause?
Yeah.
Yes. So that's a very important question, which was actually the subject of my work before doing the experiment. And the reason why I decided to do this experiment is because I had identified that the reason for this instability had nothing to do particularly with stars, but it was the interaction of waves and vortices. So I didn't put any slides to, maybe I have one slide to explain that, but so what's happening is inside a fluid like this, you have waves and you have vortices. Vortices is just like a swirl. And usually those two categories of perturbation, so vortices don't really change the depth, but there is some rotation, whereas a wave does change the depth, but in a wave there is no rotation. The motion of a wave is just, I mean, there may be rotation in the other direction, but viewed from above, a wave is a parallel propagation. And so those two kind of perturbations usually ignore each other. We call it the perturbative analysis. So when you consider small perturbations, those two kind of perturbations ignore each other. But in this kind of flow, when a vorticity perturbation is traveling towards the center, it's going to produce a wave. And this can be understood easily because if you think of this gravitational potential here, if you try to imagine a vorticity perturbation here, a vorticity perturbation here is trying to exchange a region which is deep here with a neighboring region which is less deep. You see, because the shape of the potential is deeper and deeper. If you try to make a vorticity perturbation here, you're going to take a deep region and bring it to a shallow region. And if you do that, you have to change the height of the water surface. So in a region, in an inhomogeneous flow where the depth is changing, if you make a vorticity perturbation, you are going to produce a wave. So vorticity perturbations produce waves. Okay, so what's happening then is that when waves are traveling and when a wave reaches the hydraulic jump, it's going to produce a new vorticity perturbation. This is not trivial to understand, but when a hydraulic jump is changing its shape, it produces vorticity. So you have these two ingredients where traveling waves produce vorticity when they reach the shock, and vorticity perturbation traveling towards the center produce new waves. So you have a cycle here between water waves, surface gravity waves, and vorticity perturbation, which is amplifying itself. So you have vorticity perturbation reaching the center, producing some surface wave, which reaches the hydraulic jump, and produces again some vorticity perturbation. And this new vorticity perturbation has a stronger amplitude than the first one. And so it's an amplification mechanism by which both wave and vorticity perturbation gain amplitude. And the complicated part is that this favors large-scale vorticity. So we are not talking, for my explanation here, I was talking of small vortices and small waves, but the most efficient process takes place on the large scale. So it's really the large-scale vertical motion and the large-scale wave which are going to be favored, simply because the size of this, the length scale involved in this gravitational potential favors large scales. Yes?
Have you also solved the Navier-Stokes equations here?
So for this mechanism, you don't need viscosity at all. This is an inviscid process, except, the hydraulic jump itself, in the structure of the hydraulic jump, of course, you need some viscosity. But if you idealize the hydraulic jump as a discontinuity, then you rely only on inviscid physics. But in the experiment, you have viscosity. So there is a difference between the experiment and the idealized inviscid fluid, which has some effect only in the very shallow region ahead of the hydraulic jump. In this deep region, the viscosity has nearly no effect. But it's true that in the experiment, we have to inject water slightly faster than what the slope would produce, because in this region, the viscosity is quite high. So because we expected this interaction between waves and vorticity to take place in water, then that's the reason why I decided to build this fountain. And I was lucky enough that on a small size, like 60 centimeters, viscous effects were not strong enough to kill the process. I was really lucky because sometimes you need to make a bigger experiment to make a viscous effect smaller, and if the minimum size had been 10 meters, I wouldn't have been able to do that in my garden. So this is the quantitative part of the experiment, where for different sizes of the initial radius of the hydraulic jump, I measured the oscillation period observed in the experiment, and I compared it to the one measured in the numerical simulations and also from the perturbative analysis, and the agreement was very good, surprisingly good, given the simplicity of my tools. So this is why it reached the front cover of this journal, which maybe doesn't mean much to you, but to physicists, this is very important. This PRL is a real reference. So the nice thing also is that we proposed this experiment to the Science Museum in Paris. Since it's water, people are usually inclined to try to understand what's happening with water, because everybody is related to water at home. And so it was presented to the public by my colleagues and myself during 2 months, every day. And then the museum decided to incorporate this experiment to the permanent collection. So now the staff of the museum is presenting this fountain to the public to explain the basics of supernova physics. So if we go, I will try to speed up, maybe because we were supposed to finish at 8. That's in 1 minute. So I will show you the most modern attempt to understand supernova physics. So my colleagues in Germany are really the leaders of this field, and this is one of the most recent simulation in 3D. So before I showed you some axisymmetric simulation, and this is 3D. So in black you have matter flowing at 1/10 of the speed of light and crossing this shock surface, and in the center you have the neutron star. And so in 3D you have this. You still have, for this particular simulation, a superposition of two instabilities. One is this large-scale motion, which is related to what you see in the fountain, and on a smaller scale you have convection due to the absorption of neutrinos. So this was a very important step for us, because it showed that even in 3D, with the most sophisticated physics, you still have this dynamics which we observe in the fountain. And I would like to mention the fact that Ernazar, who is here, is one of the world specialists of such simulations. So maybe he will explain to you that it's not as simple as I try to present it, because to have an accurate numerical description of this physics, you need huge computers with very high resolution. And in this series of simulations, Ernazar showed recently with his colleagues that that was a few years. No, this is very recent. So some of these colleagues are in Caltech. He showed that if you take a grid which is not fine enough, then the dynamics is very different from what you obtain with a very fine grid. Here you see very small structure. You have a turbulence you have a turbulent cascade taking place when you allow this cascade to happen. You have energy on the large scales which is able to be dissipated in 3D to the small scale. So there are big efforts across the world to distinguish what we can learn from 2D simulations such as the one I showed at the beginning and what 3D simulations reveal. We have to be careful about the specificities of different numerical hypotheses and the need for high resolution. So to conclude, I would like to show you many things, but I'm not going to show you more. But I just mentioned that now a new fountain is able to rotate to mimic the fact that the star contains some rotation at the moment of its death. So this is a fountain which is able to rotate, and surprisingly, when the fountain rotates in one direction, as here, the neutron star in the middle is able to rotate in the opposite direction. So you could give birth to a neutron star rotating in the opposite direction compared to the star which it comes from. So this is counterintuitive. This was discovered by my colleagues in Oak Ridge in 2007 through numerical simulation, but it's also something you can observe in the fountain. And the last thing I want to tell you is that if you rotate the fountain fast enough, then there is another type of instability which appears, which is this kind of spiral arm, which is able to redistribute angular momentum. So surprisingly, this fountain, which was built to study one well-anticipated instability, also contains another physical ingredient, which is currently studied through numerical simulations. So this type of instability was known through numerical simulations only before in the interior of neutron stars. And so it is something we are currently studying. So the next step is to build a bigger fountain to get rid of those viscous effects. So this is the type of size that we are currently investigating. And I will conclude. So the basics of what I would like you to remember of this talk is, first of all, that that stars die when their core reach a critical mass, and that the supernova explosion is not only an explosion, but it's also the birth of a very compact object, which can be a neutron star or a black hole. This is really the basics that you should remember. Then, if you want to remember more, you should remember that this picture first is a puzzle to theoreticians, but it's also, I mean, the way we try to solve it is to take into account that this is not a spherically symmetric process, but things are going to go sideways due to some hydrodynamical instabilities. And then those instabilities can be captured, some of these instabilities can be captured in this very simple device, which is this water fountain, where the physics follows the same laws of coupling between waves and vorticity. And if you think about it, the astrophysical content of this fountain relates to the velocity of pulsars at birth, because if you have an asymmetric explosion by conservation of linear momentum, you will have ejecta ejected in one direction, while the neutron star will be ejected in the opposite direction. So you understand that this asymmetry is related to the speed of pulsars. You understand that it will have some consequence on the spin of the neutron star, since you see, again, due to the conservation of angular momentum, if something rotates, something else must rotate in the opposite direction. And I didn't develop this here, but having an asymmetric distribution of matter around the neutron star, neutrinos, which are emitted in the inner regions, are going to be captured preferentially by some dense region in an asymmetric manner, and this is going to be a key to exceed some threshold to allow the explosion. Okay, so thank you for attention, and I answer your questions. So who wants to become an astrophysicist now? Ernazar.
Any questions?
The students will ask questions. We are older.
Yeah, go ahead.
So what is your final aim, or what do you want to? So when you just finally understand the process of explosion, what is the final target, or what do you want to? What do you want to achieve? What's your goal?
By understanding the explosion mechanism, we would like to know if the laws of physics, as we understand them, are sufficient to explain the world that we observe at such large distances. So that's the challenge that astrophysicists take, to rely on the known laws of physics to check if we understand what's happening. And if sometimes we don't understand, we are not able to understand what's happening because we are missing some laws. So the basic question is what we observe compatible with the laws as we know them? And then so usually it is, but sometimes it's not. And if it is, then we would like to know why is there a diversity of explosions, why sometimes you make a black hole, sometimes you make a neutron star. You would like to understand the statistics of how many neutron stars you form for a given number of massive stars. So you would like to be able to check that those results are compatible with the count you have of those neutron stars, those black holes. So you have many constraints, and one of the most exciting fields at the moment is what we call nucleosynthesis. So the way we generate elements heavier than iron. So this is part of them are produced during this explosion process, and part of them are not. The heaviest elements, we believe, are produced later on when a neutron star is going to collide with another neutron star, and then you will produce very heavy elements. So if you want to understand where the atoms you're made of, like gold or lead or uranium, you need to go through these different stages.
Okay, so Thierry is going to be here for 1 week. He'll be here in room 215. So if you have questions, you can meet him and have personal discussion. Okay, let's thank the speaker again. And thank you to you for coming to this talk.